up, Trig kids? Hope you guys are doing all right. And today we're going to be doing 8.5 vectors in the Cartesian plane. I just want to let you know, 8.1, that one was pretty interesting. That was pretty rough. But I just want to let you know, 8.5 is going to be much easier. Trust me, it's going to be much easier. You'll get through the online homework a lot quicker, and you'll feel a lot better about this one. Trust me. So just wanted to point that out. And for this unit, you will not need a unit circle, and you will not need the formula sheet. The only thing you may potentially need is a calculator. So as always, if you need to go to an online calculator, I would recommend eeweb.com/tool/calculator and use this calculator. Make sure in this case, your calculator, make sure it's in degrees. And of course, make sure you know how to use sine, cosine, tangent, all that fun stuff that we've talked about before. All right, so that's all you need. Let's begin. So let's pretend that we are a weather reporter and you must inform the viewers of a strong wind or strong winds coming from the west into Missouri. Now, what type of visual pictures would you use to show how big the wind is in its direction? And usually, for most people that answer this problem, they would first say, okay, over here's the west. And probably the easiest thing they would do to describe strong winds coming is that they would use arrows, saying, hey, these arrows represent the wind coming in from the west, just like that. And they probably say, oh, since they're big arrows, that means it's a big wind. But what if, say, you wanted it to be like just a small wind? Well, then probably you would say small wind means smaller arrows. So this would represent small, less strong winds coming in from the west. Now, believe it or not, these arrows do serve a mathematical purpose in this lesson. These particular arrows actually have a special name called vectors. And that's going to be our main topic today is how do we work with these vectors, how do we mathematically calculate them, and how do we draw them as arrows on an XY plane. So, just to give you a little more introduction to what vectors are, they are a visual. Vectors are a visual, or in this case, we'll let them be arrows. They are visuals of a given force that tell us two things. They tell us the direction of the force and also the strength and magnitude of the force. Now, when I'm talking about force, I'm talking about anything that produces energy, like wind. Like usually wind is probably the best way to describe it. So let's say we need to talk about direction. Well, of course, vectors or arrows, you can have them point in any direction. You can have them point to the left. You can have them point in the other way. I just got my left and rights wrong. Sorry about that. And of course, you don't have to go left or right. You could have it pointing upwards. You don't even have to have pointed out upwards. You can go downwards. Heck, you can even go diagonally. Diagonally downwards, diagonally upwards. I think you get the idea. Basically, vectors point in the direction that it's going. But another thing we've got to talk about is vectors tell us the strength or magnitude of our force. Like, for example, let's say we had a bunch of itty-bitty arrows. Not really concerned about direction, just look at the itty-bitty arrows. If you had smaller arrows, you would probably think, okay, this is a weaker force because the arrows are smaller. But of course, the exact opposite, or in other words, bigger arrows or longer arrows would tell you the exact opposite, meaning that this would be a stronger force. So that's what vectors do. They point in a very specific direction, and depending on how large your vector is, that'll tell you how strong the force is. The smaller the arrow, the weaker the force. The bigger the arrow, the stronger the force. And that particular word, determining how strong or weak our force is, that is called magnitude. And that's something we will come up later in this video, is magnitude. So now you got an idea of what vectors do. Let's talk about notation. Vectors, in terms of mathematics, are usually expressed as lowercase letters. So in other words, if you see a lowercase u, that would be the notation for a vector. And on the graph, they will always have a starting point and an ending point. So in other words, let's say we have vector u equal to the arrow point P, point Q. Point P, which in this case would be this point right here, would always represent the beginning point, or B for beginning. The second letter Q would represent the ending point, or in other words, basically where your arrow is going to be pointing. So B for beginning, E for ending. The first letter is always the beginning, the second letter is always the end. And these two letters, as always, will give you the beginning point and the ending point, as you see over here. So that will be a big help, realizing what your beginning point and your ending point is. Now, if I were to ask you how to numerically describe the direction of the vector, or more importantly, what if I were to ask you, could you explain to me in numbers what direction that arrow was pointing? Well, some of you would probably say, looks like it's going northeast. It's going in the northeast direction. But wait a minute. I said, can you describe it to me in numbers? Northeast is not a number. How would we describe the direction of that arrow using numbers? And that is what's on the next slide. On the next slide, we have vectors u, v, and w, but they're written a little bit differently. They're not written as point P times point Q. Instead, they're written as a component form. And what the component form of a vector is, it describes the direction by giving the x movement and y movement of the vector. So in other words, some of you may be thinking, oh, is this the same thing as point P, point Q? It is not. What's happening here is basically the first number is going to tell you what direction to move, left or right. And then the second number is going to tell you which direction to move, up or down. And usually your hint to determine this is the component form is the component form will always have these triangular brackets. Not open, not closed, triangular. Kind of like they look like little arrows. You can see here that kind of looks like an arrow pointing to the right, and this is an arrow pointing to the left. That should be your cue. Oh, arrows, vectors. This is a vector. So now let me show you exactly what we're doing here. So let's say we need to specifically draw vector u. And I'm going to go ahead and start here. The 6 is going to tell me to move left or right. And instinctively, since the 6 is positive, your gut is probably telling you, I should go to the right 6 units. 1, 2, 3, 4, 5, 6. Yeah, it's kind of hard to see the XY graph in this plane, so just bear with me on that. So 6 units to the right, because that's 6 units in the positive direction. Now the -4 will tell me to go up or down. Well, which way do I go, up or down? That'll depend on the negative. The negative, your gut feeling will tell you that you need to go down 4 units. So from here, go down 1, 2, 3, 4 units. All right, you've moved to the right 6 down 4. Now connect the 2 dots. That's your vector u. So that's how you describe the direction in numbers. Or in other words, this number will tell you which way to move left or right. This will tell you which direction to move up or down. So in other words, this is what all the vector u's will look like. Like let's say you have a vector u up here. Again, it's going to look just like it. 6 units to the right, down 4. Let's say you want to put a vector right here. 6 units to the right, down 4. Again, it's going to look just like vector u. Again, I'm just trying to do this really quickly. They probably don't look exactly like u, but I think you get the gist. All these arrows are going right 6, down 4. So now you see where the direction of the force is going. Now let's try the other two, doing something very similar. Now let's say we want to draw vector v. First, we'll look at the -5. The -5 will tell me which way to go in terms of left or right. The negative looks like it's going to tell me to go to the left. So 1, 2, 3, 4, 5 units to the left. The 7 will tell me to go up or down. In this case, the 7 is positive, so that your gut feeling should tell you should go up 7. So 1, 2, 3, 4, 5, 6, 7. So 5 units to the left, 7 units up. Whoops. And then connect your 2 dots, your starting and your ending. And that's what vector v is going to look like. Doesn't matter where the vector v is, but each arrow will be going to the left 5, up 7, just like vector v. So there you go. That's how you would tell the direction of that force. All right, let's do one more, just to show you how this works. Now let's do the same for vector w. Again, the first number will tell me which way to move left or right. In this case, the 1 is positive, so that means I'll move 1 unit to the right. And then the 0 can't really move up or down when you got 0 units. So it looks like we're not moving up or down at all. So it looks like that's it. A small little arrow going to the east. And that's what all those arrows will look like. Just 1 unit to the east for each arrow. That's it. So if you always think of it that way, the first number tells you to move left or right, the second number will tell you to move up or down. Then you basically know how to draw a vector and exactly which direction it's going. And also, if you think of it, it also tells you what the magnitude is, or the strength. Because you saw with the other two, they were actually pretty big arrows, meaning they have bigger forces or bigger magnitudes. This one, vector W, looks really tiny, which means it's probably a weaker force or weaker / smaller magnitude. And speaking of well, we'll talk about magnitudes later. So now, moving on, let's say that how about this time, I need you to find what the component vector is. I need to find exactly what number will move me left or right, and what number will move me up or down. Well, to do that, here's the formula. You're going to first have to determine your start point and your end point. Your starting point, you'll label it x1, y1, and then your ending point, you'll label x2, y2. And once you have those labeled, to find the component form, you first do x of 2 minus x of 1. That'll give you the left or right number. Then you got to do y sub 2 minus y sub 1, and that'll give you the number that tells you to go up or down. Easy as that. For some reason, you guys probably recognize it too, but this is kind of reminding you of the slope formula, right? Like if you had y sub 2 minus y sub 1, yummies on top, then you have your picnic table legs on bottom, y sub 2 minus y sub 1 right here, x sub 2 minus x sub 1 right here. That's not a coincidence. Just wanted to let you know. But anyway, now let's put that formula to use. So let's say we have this example. We're given 2 points. Find the component form of the vector. And we're going to assume that the first point is the initial point and the second point is the terminal point. Now what this means, initial point means the beginning. The terminal point means the ending. So it's basically telling us that the first point is our beginning. Our second point is going to be the ending point. So with that in mind, before we start, let's go ahead and label. The beginning point will be x1, y1. The ending point will be x2, y2. And remember, we are trying to find the component form. Or in other words, in this case, we'll call vector u. We're trying to find this form. And according to the previous slide, you got to do x of 2 minus x of 1, and then y sub 2 minus y sub 1. And that's how you find the numbers of the component form. So let's go ahead and do it. X of 2, in this case, will be -8, and then minus x of 1, which in this case is -6. So we got a minus a negative here. That will change things. Y sub 2, we got to be 8 minus y sub 1, which is 0. All right, now you just do the math from here. So you got -8 minus a -6. Minus a negative will make that plus positive. So now you just got -8 plus 6, which gives you -2. And that will be your number to tell you to move left or right. Then the second number, 8 minus 0, will give you 8. That will be the number to tell you to move up or down. So in other words, the component form of vector u, using the vector arrows, or the vector parentheses, will be -2, 8. Easy as that. Much, 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 much easier. All right, let's do the same thing for the second one. Same thing. We need to find a component form. The first point is the beginning. Second point is the end. So the beginning point we will label as x1, y1. The end point we will label as x2, y2. And again, if we need to find the component form, got to use the formula x squared, x sub 2 minus x sub 1, comma, y sub 2 minus y sub 1. Follow the rest from there. X sub 2 will give you -4 minus x sub 1, which is just a regular 4. Y sub 2 will give you -9, and then minus y sub 1, which will give you 2. All right, plug and chug from there. First, we'll do -4 minus 4 to give you -8. And then -9 minus 2 will give you -11. And that's your component form. Easy peasy. All right, so now you know how to find the component form. Now, I need to show you how to find the magnitude, or to find how small or large a vector force is. So, finding the vector magnitude. Vectors not only give direction, the length of the vector tells us its power or its magnitude. So in other words, these three arrows are not the same. Yes, they all point in the same direction, but the sizes are all different. So in other words, a smaller arrow means that you have a weak magnitude or force. The middle one would be probably average magnitude or average force. And then, of course, the last one, since it's larger, it would have a strong magnitude or strong force. But, of course, if you want to numerically find just how strong or how weak a magnitude is, it is used by this formula. So first, if you ever see a vector with these two bars on the left and the right, that is the symbol for magnitude or force. And to find it, you got to do the square root of a squared plus b squared, where a is going to be the number that tells you to go left or right. B will be the number from the component form that tells you to go up or down. And it's as easy as that. That's how you find the magnitude. So let me show you some examples of where we do this. So we're given this vector, and it's defined by these points. So say you have these 2 points, and we need to find its magnitude. And typically on the Hawks program, when it asks you for the magnitude, it's going to ask you to do 2 steps. The first step it's going to ask you to do is to find the component form. And, well, you guys already know how to find a component form from the previous examples, so I went ahead and did it for you already. Here's a component form of this vector. But now the second step is where you'll actually have to use the magnitude formula. So the absolute value, or not the absolute value, the magnitude of u, which means you have 2 straight arrows left and right, is going to be equal to the square root of a squared plus b squared, where the a comes from the first number, the b comes from the second number. So let's go ahead and try it. So we're going to take the square root of a squared, which will be negative 2 squared, plus b squared, which is going to be 8 squared. Simplify from there. Negative 2 squared will give you 4. 8 squared will give you 64, which will then, if you simplify, give you the square root of 68. And technically, you have the magnitude. Technically, you are 95% done. Ms. Shulin, I don't like it when you say 95%. That means that there's always something more we got to do. And it turns out, for the Hawks program, if the root can be simplified, it will want you to. So in other words, if you can break it down into the multiplication of 2 roots so that one of these roots is a perfect root, it will want you to do so. So for this example, it turns out 68 can actually split up to 4 times 17. 4 times 17 is 68. And the reason why we want to break it up like this is so that now we have a perfect root. The perfect root of 4 is just going to be 2. And then the square root of 17 will just stick along in the side. And this cannot simplify anymore. The square root of 17 cannot break down since it's prime. So then we can finally say that this is our final answer. And this is what will go into the Hawks program, or into your Hawks homework. So that's the magnitude. That's how strong that force is, or specifically that arrow. Let's try another one just to get a little comfortable with the magnitude formula. So, again, let's say you're given these 2 points and you need to find the magnitude. The first step you'll need to do is to need to find the component form. But again, you guys know how to do the component form. We did those on the previous 2 examples, where you do x of 2 minus x of 1, y sub 2 minus y sub 1. You guys know how to do that already. I went ahead and did all that work for you. So now that we have the component form, we can now move on to step 2, which is to find the actual magnitude. So the magnitude of u, again, square root of a squared plus b squared, where the a is going to be the first number, the b is going to be the second number. So let's plug and chug. So square root of a squared, which will be negative 8 squared, plus b squared, which will be negative 11 squared. Go from there. So negative 8 squared will give you 64, and then negative 11 squared will give you 121. Add those together, and that should give you 185 for your magnitude. And then it's up to you to see if we can break this down so that one of these is a perfect root. And of course, if you need to, you might need to make a list of all the perfect roots to see if any of them are multiples of 185. But I will let you know, you can try all you want for this one. This one cannot break down. This one cannot have a multiple of a perfect root. So in other words, you can keep this answer as the square root of 185. So sometimes you can break them down, sometimes you cannot. You just have to try and see what you can do. And there you go. That's the magnitude of that vector. All right, we're halfway done with the video for now. I will have this video split into 2 parts. I'm just covering the easy stuff for part 1. So now that you know what the component form is, you know what a magnitude is, now let's talk about some other specific examples. So let's say you were given a vector, but you weren't given its direction. You were only told that it has a magnitude of 5, or it has a magnitude of 5 units, and you were also given that its angle from the origin, in other words, the angle it makes from the beginning, is 90 degrees. So in other words, that tells you, oh, this arrow has to be pointing straight up because 90 degrees. Now, how would you find the component form of this vector? Or in other words, how would you be able to determine how it moves left or right, up or down? Well, I'm sure some of you can actually just look at this and determine what the component form is. Like, for example, it does not move left or, if you look at the blue arrow, it does not move left or right at all. So in other words, you would say 0. But the magnitude tells you that you're supposed to have 5 units, or magnitude of 5 units going upwards. So that'd probably tell you you have to do 5 units up. Some of you probably already realized that. It's obvious. It's 0, 5. Now, sometimes it's not that obvious. Sometimes we need something a little bit more concrete to help us find this component form. Now, just to show you what I'm talking about, there is a formula that will always help you find the component form if you're ever given the magnitude and the directional angle. So, again, if you're ever given the magnitude of a vector and its directional angle, you can find its component form using this formula. So in other words, to find its component form, again, using the arrow parentheses, you'll first have to take the magnitude times cosine of the angle, and that'll give you the answer that tells you to move left or right. Then, if you take the magnitude and multiply it by sine, that will give you the number that tells you to move up or down. So this formula will help you find the component vector every time. So, let's try it. Let's give it some use. So, let's say we had that original vector that we looked at with magnitude of 5 and a directional angle of 90 degrees. Let's find the component form using this formula. So in other words, I'm going to have to do the magnitude, which is 5, and then I'm going to times that by cosine of the angle, or cosine of 90 degrees. Then, to find the second number, I'll do the magnitude, which is 5, and then multiply it by sine of 90. And then let's see what happens. So if you take a look at the calculator, you'll first do cosine of 90 degrees, which should end up getting you 0 when you do cosine of 90. Then you'll do 5 times sine of 90, and sine of 90, if you put that in your calculator, that'll give you 1. So do the rest from there. First you do 5 times 0, which is just 0, and then 5 times 1, which is 5. And that is the component form of the vector. Check it out. That's the same component vector that we found by looking at the graph. So you know that this formula works because it got you the exact same component form. Done. Piece of cake. All right, let's just try another one because they're not going to be as clean as this one was. Not always. Or brace yourself, we're about to get some decimals. So now we're going to find the component form of this vector. Let's call it vector v. And we're going to use this formula with the magnitude of 17 and the angle of 140. So let's go ahead and plug the numbers in. So first I got to do the magnitude of 17. I'm going to times that by cosine of the angle, which in this case is 140. And I tried looking at the unit circle. Actually, 140 is not on there. So we have no choice but to plug this in the calculator. All right, for the next one, absolute value, or not absolute value, magnitude of v is 17. And then times that by sine of the angle, which is 140 degrees. All right. Brace yourselves. When I do cosine of 140 degrees, you're going to get some really long, nasty decimal. And you are not to round it. You do not round until you get to the final answer. So if you do cosine of 140, let's see what we get in the calculator. Gotta do cosine of, oops, try that again. Cosine of 140. Oh, close parentheses. You're going to get that nasty decimal. And you're going to need to use as many decimals as you can. So let's do it. So write down negative 0.766044443 119. I know you guys don't like that. You guys want to go ahead and round it, but you can't round not until the final answer. I'm sorry. Okay, now we got to do the second one. 17 times sine of 40. Sine of 140. All right, let's see what we get. Sine of 140, close parentheses, gives you that. Okay. I need to take a picture of that, or I need to write that on the board. 0.6427876096865. Got it. All right. All right, let's write that all in. 0.6427876096865. Yeah. Okay. But never fear, once we multiply those numbers by 17, we will then be able to round. So now we're going to do 17 times this decimal. So take that huge decimal, times that by 17, and whatever that answer is, now you can round it. And we should probably look, how many decimals can we round to? Round to 4 decimal places. All right, so let's round to 4 decimal places. You'll get negative 13.0228 when you round. All right, now let's do 17 times this disgusting number. All right, take that huge number times 17, and you should get 10.9274 when you round to 4 decimal places. And that would be your component vector. Yeah, so that one was not as fun as the previous one. And sometimes they will be like that. So with these examples, please take your time, write down every decimal, do not round until you get to the final answer. You will definitely need to take your time and double check these examples just so you don't make a tiny error. But besides that, that's how you use that formula. Before I end the video, just want to show you another quick example. So let's say they've already plugged in everything into that formula. Given this information, you're going to find the magnitude and directional angle. Now basically what's happening here is they've already done that component form formula that we just worked with. But what they've done here is that they've actually factored out the magnitude out to the front. But if you distribute it back to where it should be, it will look just like you did for the formula. And just so you know, for right now, ignore the I and the J. We'll talk about that in the next video. Don't worry about those right now. What this question is literally asking you is, what is the magnitude and what is the angle? And literally, if you look hard enough, it gives you those answers right there. I just told you the magnitude is this number here that gets distributed. So you know that the magnitude is going to be 14. Done. And the angle, well, you can probably guess what the angle is. It's going to be 83 degrees. My warning is that you must put the degree symbol. If you just put 83 without putting the degree symbol, the Hawks program will count it wrong. And no one wants to miss a point on this easy example. So please, 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 please put the degree symbol. Do not forget it. And that's literally it. That's like probably the easiest problem in the book. So like for this example, the magnitude, if you distribute it, the magnitude will be 7. And then your angle, 53 degrees. Again, put the degree symbol. And that's it. Easy peasy. So just wanted to introduce you to some easy stuff with the vector mathematics. We'll focus more on some more interesting examples in the next video. But for now, I will bid you guys adieu.